All right, well, welcome back. Now we're going to look at linear systems in 3 variables. So we're going to up our 2-dimensional conversation into a 3-dimensional conversation. So solving a linear system with 3 variables, we could review what we just talked about, which was 2 variables, x and y. If they are lines, they would be to the first power. And so each equation in that case would represent a line in 2-dimensional space. And so we wrote our solutions as a point in 2-dimensional space or as a set of infinitely many points on a line, right, if the lines were overlapping. In this section, we're going to be dealing with 3 variables, x, y, and z, and we're going to have 3 linear equations. Because we now have 3 variables, a line, if I extend it into a 3-dimensional space, becomes a plane. I always describe a plane like a piece of paper that's infinitely thin and spreads out in all directions. So we're going to be looking at how 3 planes can interact in 3-dimensional space. And I want to show you this diagram that's in the book on page 424. It makes a really good visual aid. But if those 3 planes could intersect at one point, and so we're going to write our point with 3 coordinates, it's called a triple, x, y, z. If we don't have enough information or they don't intersect at one point, then they may intersect at a line. And so we're going to write our solution a lot like we did in the last video with one arbitrary variable. And if these planes intersect, I guess maybe if they overlap, then we could write our solution with 2 arbitrary variables, and so we take some time to look at what that would look like. So let me show you this diagram. This is on page 424. Hopefully this will be an easy thing to do for you. I'm not sure how I can get it under the camera. Let's finagle it here. Okay, let's try that. All right, so 3 planes. This looks sort of like this. Notice how these 3 planes intersect at that one single point. Okay, or we could have 3 planes sort of organized like this, and what they have in common is that line there down the center. So that's where we would use the one arbitrary variable. Or just like with the lines, the 3 planes could completely overlap and actually represent the same plane. In that case, we would use 2 arbitrary variables. Okay, this would be if we got a solution. If it's inconsistent, these are like several different ways where it could be inconsistent. So maybe the 3 planes are like parallel. In that case, they don't share anything. Or maybe 2 of them are parallel and the other one is sort of transverse, is that the word? Cuts through the other 2, but they still don't all 3 share a common point. Or they could look like this, okay, or 2 of them could overlap, but not the 3rd. All right, so here's just some examples where we would get no solution. Okay, so now let's talk a little bit about the strategy for solving a linear system with 3 variables. All of this is summarized in your book, and I've tried to put in some page numbers in case you want to go back and read it. Look at their examples, which I always recommend. I love this book. So for 3 variables, we can use some of the same tools that we talked about in the last video, like substitution or elimination. So if elimination is one route, and this is sort of what they suggest, we can take one pair of equations and eliminate a variable. I'm using the word eliminate here. So we can do elimination, but we could also do substitution to achieve that goal. Okay, and then with step 2, we want to take a second pair of equations, not the same pair, a different pair, and eliminate the same variable. So if I choose, I think in a minute we're going to do an example where we eliminate x. So I pick a pair, I eliminate x, I get a new equation with y and z, and then for step 2, I pick a second pair of equations. I also eliminate x, I get another equation with y and z. So then in step 3, I'm going to take those 2 resulting equations that I got from the first 2 steps and solve that as a system, just like we did in the previous video. It sounds more complicated than it is. It is a little bit long, but it does work, and it is nice to have a step-by-step sometimes. So, all right, so let's try it out. This is a problem number 17 from your book. So solve the system with 3 variables. Okay, so let's do what we just said. We'll label these 1, 2, and 3. We can pick any variable to eliminate. For whatever reason, I have chosen X in the past, but really any of these would work just as well. I'm going to stick with X today, but if you want to try this out with a different variable, by all means, go right ahead. And we should get the same result. Okay, so I'm going to eliminate X using, let's start with equation number 1 and equation number 3. That looks like a good choice because the coefficients in front of X are already equal but opposite. Now, I'm using elimination today just because I think that may be a little bit quicker for me, but substitution works just the same. You could solve for X in equation number 1 and substitute what you got into equation number 2 or 3, and thus eliminating X and giving you the results that you would need. Okay, so here is equation number 1. I'm just copying it down because I don't need to do any multiplying this time. And here is equation number 3. And I'm going to add them together. And the x's are going to be eliminated. So I'm going to have negative 4y plus 2z equals 0. Okay, and that is an equation I want to hold on to. I'm going to come back to that one in a minute. All right, so that was step 1. Now I want to pick a second pair of equations and eliminate x again. And because this one's negative, I think I'm going to go with 2 and 3 this time, so that I already have the opposite going on. So now I want to eliminate x. Using equation number 2 and equation number 3. This time I'm going to need to multiply equation number 3 by 3. So I'm going to copy down equation number 2. And I'm going to multiply equation number 3 by 3 all the way across. So that's going to give me negative 3x minus 3y plus 12z equals 9. And I'm going to add those together. I'm going to eliminate x again. And when I add these, I'm going to get negative 1y plus 11z equals 21. Okay, so now I have 2 equations. Circle them so you can. This guy and this guy. And now I want to take these 2 equations together as a system and solve with either substitution or elimination. Okay? So that would be step 3. So I'm going to move this down. I'm kind of done with the first 3 equations for the moment. We're going to just be focusing on these 2 that we created. So let me write them down. You could label them 4 and 5 if you want to. I'm not going to do that today, but if you wanted to, you could. Okay, let's say we're going to eliminate y. So maybe we could multiply equation number 2 by -4. Since -4 times -1 would make this a positive 4y. And then I could add these together and then the y would get eliminated. So I'm going to do that. So I'm going to copy down, I should indicate that somehow. So I'm going to multiply this by -4. I'm going to copy down the first equation. And then I'm going to multiply the second equation by -4. So that's going to give me 4y minus 44z equals -84. That's going to eliminate my y. And it's going to give me -42z equals -84. Now I'm down to one variable, which is sort of what I've been working towards, because remember, even when I have 3 variables, I can still only solve for them one at a time. So now I'm down to one variable. I can solve for z. It looks like z must be 2. Okay, once I've gotten one variable, I can go back and substitute for the other 2 to get the y and the x to go along with. Okay, and this part's called back substitution usually. I'm just going to try and see if I can squeeze this all in on one piece of paper. So I'm going to come all the way back up here. This has a second column. All right, so I just found that z is 2. So it would be wise to use one of these 2 equations to find y next. It doesn't matter which one you use. I'm just going to use this first one, not for any good reason. So now I want to solve for y. So I'll have -4y plus 2 times 2 equals 0. That's 4. I subtract 4 over, I'll have -4y equals -4. If I divide both sides by -4, looks like y is 1. Okay, so I have y and I have z. Now I need to find x. Now I need to go all the way back to the beginning. One of these 3, remember this is a common point, so it doesn't matter which one we use. Because this is just x by itself, I think I'm going to use number 1. But any of them would work the same. When I go back to solve for the last variable, I have to substitute for both y and z. I'm going to have x minus 3 times 1 minus 2 times 2 equals -3. So that's x. This will be -3 and -4. So -7 equals -3. If I add my 7 over, x must be 4. And I'm going to write my final answer as a triple. So my solution is the triple 4, 1, 2. Okay, so that's the process, right? And we really did work through those 3 steps. We eliminated one variable with 2 of the equations. We took a separate pair, eliminated the same variable. We took those 2 equations and did elimination, although we could have done either substitution or elimination. We solved for one of the variables. Then on the right-hand side here, we did all the back substitution to get all 3 variables, and we wrote our final answer as a triple. Okay, here's a really common application of this type of problem. I use the word application a little bit loosely here since we are solving for something that is mathematical, but it is some way that we could use this idea. It says find a quadratic function whose graph is a parabola containing the 3 points listed here. Okay, so in this case, we know the value for x and y because we have these 3 points, but we don't know the coefficients for the equation of this parabola. We don't know the a, b, or the c. And so just so you know where these 3 equations came from, I already built these for us. If I plug in these points for x and y, I'm going to get the equation over here, right? So if I plug in -1 for x, I'll have a times -1 squared plus b times -1 plus c is equal to the y value, which is 9. But -1 squared is just 1, so really this is a minus b plus c. That's sort of where this came from, right? And I did that for all 3 points. Each point gives me an equation. The next one would look like this, where I'm plugging in x to be 2. Okay, 2 squared is 4, which is where this came from. 2b plus c equals the 6, which is the y value. Likewise for the last one, I plugged in 3. And that's where that equation came from. So now we have a system of 3 equations, 3 variables. So we can work it out just like we did the last example. We want to choose, let's name these 1, 2, and 3. We would like to choose a variable to eliminate. Any of these would work just as well, but I'm really thinking C might be a really good option because we have the plus C in all 3 of these. Just realizing that now. So let's do that. Let's eliminate C. We'll start with the first 2 equations. Now you have a lot of options here. So don't think that this is your only choice, because it's not. Just happens to be what I'm choosing today. If you want to try it out a different way, by all means, I want to encourage you to do that. Okay, so I'm going to keep equation number 1 the same. But to eliminate C, I need to have a negative C in the next equation. So I'm going to multiply equation number 2 by -1. And then I'm going to add them together. The C's are going to be eliminated. And I will have, let's see, this is 1 minus 4, so -3a minus 3b equals 3. Okay, then I want to do the same thing. I want to eliminate C from a second set of equations. It doesn't really matter. Again, it really doesn't matter which 2 we pick. We just can't pick the same pair. How about, I don't know, how about 2 and 3? Okay, so here's equation number 2. I'm going to do the same thing. I'm going to multiply equation number 3 by -1 so that this becomes a negative C. I'm going to add them together, which will allow C to be eliminated. And I get -5a minus 1b equals -7. Okay, just like before, we are now going to be dealing with just these 2 equations. Notice I've gotten rid of C for the moment, and I have 2 equations that deal only with A and B. Right, so now I would want to take some time to solve that system. guess we'll go down here like we did before. So if I write those out, you could label them 4 and 5 if you want, like we've talked about. It's looking like maybe eliminating B would be the easiest. So I'm going to multiply this, call it equation 5 if you like. Multiply this by -3. So that when I do that, this will be a positive 3B, and the B's will get eliminated. Okay, so that becomes, so I'm going to eliminate B. So I'm going to leave the first equation the same. I'm going to multiply the second equation by -3, so that's going to become 15A plus 3B equals 21. I'm going to add them together, and that's going to give me 12A equals 24. I'm going to divide by 12 on both sides. I'm running out of space here. This space is in the bottom. Looks like A turns out to be 2. Okay, and that makes us super happy because we've gotten one variable. Now we just need to do the back substitution to get the remaining variables. Just like before, I'm going to go ahead and come all the way back up here to the top. I just found that A is 2. So now it would be wise to go back to one of these other equations to solve for B first. I'm just going to use this first one, not for any good reason. Remember, it's a common solution for both of these, so you could use either one. I'm going to put in A to be 2. This would be -6, and if I were to add it over, would make -3B equals 9. Dividing by -3, B must be -3. Then last, I want to take both of these and go back to one of the original equations to solve for C. And I'm going to go back to the first equation just to make it a little easier, so that'll be 2 minus -3 plus C equals 9. So really that's 2 plus 3, so 5 plus C equals 9. If I subtract 5 over, looks like C is 4. Okay, normally I would write the solution as a triple, but remember the context of this problem is to go all the way back to the top. Find a quadratic function that looks like this. So instead of writing it as a triple, I'm going to write it as a function. So the parabola that passes through all three of those points would be y equals 2x squared minus 3x plus 4. Okay. One more example for you. So now let's say we want to solve a linear system with 3 variables, but only 2 equations. Okay, well, I know that looks like there's 3 equations here, okay, but we'll talk about that. All right, so the intersection of 2 planes will be a line. And so if this boils down to effectively 2 planes, which is what's going to happen, then the solution set will be all the points, infinitely many points lying on a line. And so we want to write the solution with an arbitrary variable, and we're going to use the variable z as the arbitrary variable. Okay, and so here's where having a little bit of foresight might help you out. If you could look at these 3 equations, one of them is actually a multiple of the other. So if we were to start doing elimination, we would see that, right? So maybe we didn't notice it at first. Maybe we just said, I'm going to eliminate x in equation 1 and 2. So let's start by trying that. Okay, if I were to eliminate x, I would need to multiply the first equation by -2. So let's do that. That becomes -4x minus 2y plus 6z equals 0. And then I'm going to copy down this second equation. This is another one of those cases where I set out to eliminate one variable, x, but I accidentally eliminate y and z all at the same time. So I get 0x plus 0y plus 0z equals 0. All right, and we want to look to see if once the variables have all been eliminated, do I have something true or do I have something false? Just like in the past, if I had something false, I would immediately say there's no solution. Okay, but I don't have that. I have something true, which means that these two planes are overlapping. So equation number 1 and equation number 2 are effectively the same, which means I don't really need to have both of them. I really just need to have one of them because they're the same plane. And then they don't match up with equation number 3, so I really need to solve the system of these two equations. So at the very top, let's go back up just for a second. We said, okay, we're going to solve a linear system with 3 variables and only 2 equations. So this could happen when we see 2 of them as overlapping planes, or maybe we're just given 2 equations. Okay, and so in this scenario, the intersection of these 2 planes will be a line, and we're going to write this with z as the arbitrary variable. Okay, so now we could rewrite this system. Oops. We could rewrite this as the first, I'll do the first equation, which is actually standing in for both the first and the second since they're overlapping, and then the third equation. Okay. So I guess at this point we would want to start out by eliminating a variable, and I think the most obvious choice here might be y. So we could eliminate y pretty easily. All we have to do is add these two together, right? And that's automatically going to eliminate y. So do I need to rewrite them here? Or can we just add them together? I'm just going to shortcut here and add them together. Okay, so 2x plus x would give me 3x. Y plus negative y would give me 0y. Negative 3z plus z would give me negative 2z equals 0. All right. Here's where the arbitrary variable comes in. I'm not going to be able to solve any further to get a number for x or y or z, but I would like to represent everything in terms of z, which is going to be my arbitrary variable. So I'm going to solve for x. I'm going to add my 2z over to the right-hand side. And divide both sides by 3. So I'm going to write x as 2/3 z. That way, when I have any number for z, I'll automatically have an x value that would put that point on that triple on the plane, or sorry, not the plane, on the line where these two planes overlap. Okay, I want to do the same thing for y. So now I'm going to go to one of these equations, doesn't matter which one, and I'm going to substitute x to be 2/3 z. Okay, so I did eliminate y, and I sort of did two things together here. And I also solved for x. Now I'm going to go back and solve for y. Trying to decide which one would be easiest. Okay. I guess I'm going to use the first one since the y is positive, but either of these would be fine. So I'm going to put in x to be 2/3 z. And I want to solve for y. So this is actually 4/3 z plus y. Let's write this as a fraction over 3. Can we do that? Think of this as 3 over 1. So multiply top and bottom by 3. This is the same as 9/3 z. Just trying to make the math a little easier for us. Okay, so if I combine these, really this is y minus 5/3 z. And I'm going to add that 5/3 z over to the right-hand side. Okay, so I'm going to write my solution. Let's describe it a little bit, right? So these, the solution is a line with infinitely many points. Okay, it's actually a line in three-dimensional space. So we're going to write this generic point that's on the line using z as our arbitrary variable. So we're doing 2/3 z for x, 5/3 z for y, and just z for the z. Okay, so if I were to plug in, say 3 for z, right, I would get 2, 5, 3, and that would be a point on this line where the planes intersect. If you wanted a visual, can I get that out real quick before we finish? You could go back to that page we looked at earlier. Here it is. Let's see, which one of these? Nope, none of those are pictured there. Bummer. Alright, I was kind of thinking of this one because two of the planes overlap. Notice it says 1 and 2. That's kind of the scenario we had, but the third plane actually did intersect that overlapping of two planes. And so we did get a line. It would be sort of like this one if plane 1 and 2 were condensed to be the same. Okay, well, I tried. All right, well, I hope this gave you a good idea about how to solve a system with 3 variables. This is definitely something that's going to take a lot of practice, so I hope you'll take some time to practice this and get comfortable with it. Good luck.